here, by this, I mean, how can we have this 4 adjacently occupied sites? And of course, let's start from the very basic. As I already mentioned, each site here is occupied with the probability P. It means that for us to have these 4 adjacent occupied sites, we have to have this. The first site should be occupied, and second is also occupied, and occupied. So it will be proportional to p to the 4th power or something. Is this the right answer? Let's think about it. It has some kind of element, but is this enough? What do you think? So actually, what I try to emphasize here is that if we just write down, hypothetically, if we just write down this probability, it means that if we take just the 4 adjacent sites and the probability that all of them are occupied. But one tricky part is that this probability does not include the different cases of these other sites. So it includes, so of course it's this p to the 4th power, the p to the power of 4, p to the 4th describe this situation. But if we just write down this probability, it can describe this one, or this one, or this one, or this one. Because we don't care about the other site is occupied or not. So actually, if we just write down this probability, actually this overestimates the possibility of the size 4 cluster. Because we try to calculate the probability of a size 4, but the real situation where we have a cluster of size 4 is this one. Because of course, the cluster of this site is actually 6. But actually, 6 plus alpha, because we don't care about other things as well. At least 6. And of course, 5 plus alpha and 5 plus alpha. So to have a cluster with exactly 4 sites, to have a cluster with exactly 4 sites, we have to pinpoint this particular case. It means that along with the 4 occupied sites in the middle, we have to have this unoccupied sites right outside of this cluster. So of course, then we have to modify this probability. Again, I would like to emphasize that each site is occupied with the probability P and unoccupied with the 1 minus P, right? So it's a 1 minus P times P to the 4th, and again 1 minus P. And this is the answer, because we don't need to care about all the other part of the lattice. So this is the probability to have exactly 4 site components. So this is the first kind of non-trivial mathematical derivation in this book. So that's why I took some time to explain it to you, and it's always a good exercise for you to try to figure out yourself about this thing. So in general, of course, so according to this logic, in general, the probability of the cluster with the size S is of course 1 minus p squared. This is a default one for boundary part, and p to the power of s. Yeah. So this is exactly the exact probability of a cluster with the size S. So unoccupied, occupied, and again unoccupied. Yeah. And you can imagine or hate to imagine that the more complicated system, like a two-dimensional system, these parts can be very complicated. And this part as well, actually. Because again, because this system is so simple one-dimensional system, you can just multiply like this. But if you imagine like this kind of a two-dimensional system, you don't need to have this fully occupied site for the size 4 cluster. You can have this one, or this one, that will remind you of the Tetris block again. But yeah, that's why we are really, these problems are so closely related to each other. So because we use this very simple one-dimensional percolation, we can have this very general, the most general formula easily. Yeah. That is important point.